So, having established the velocity scale for this particular problem, let's write down the velocity g beta d square t naught minus t infinity divided by 8 gamma 1 minus x by d by 2 square. That was a velocity scale that we extracted. Okay. So, now in order to calculate the heat, okay, let us calculate what is the mass flow rate per unit length normal to the plane. Okay. So, normal to the plane. So, m dot therefore will be equal to rho g beta, because it is basically rho a v and that kind of stuff. So, it is basically dA cube T naught minus T infinity divided by 12 gamma. Okay. So, so m dot basically we have found it through rho a into Vm. Vm is the average velocity. Okay. So, in order to calculate the average velocity, you need to just integrate this guy, right. Okay. So, that will give you rho a into the corresponding Vm. Okay. So, that is how that integration you can do, okay, as an exercise. Okay. It is just integration from 0 to d by 2, right. So, that is all the integration is there to it. Okay. So, now the total heat transfer rate between the stream and the walls, right, total heat transfer rate between the streams and the wall. Okay. So, between the streams and the wall, which is given as q prime, say, is m dot Cp, all right, multiplied by T naught minus T infinity, correct. Okay. So, it is m dot Cp T naught minus T infinity. So, in other words, q prime therefore becomes, because we already evaluated your m dot for u. Okay. So, it is basically Cp rho g beta d cube divided by 12 gamma T naught minus T infinity square, right. Already there was a T naught minus T infinity in the m dot term. So, it is basically square of the two. Okay. So, the average heat flux, that flux term, okay, q double prime will be equal to Cp rho g d cube into beta divided by 12 gamma by 2h T naught minus T infinity square. Okay. T naught minus T infinity square. Okay. So, it is basically nothing but q double prime is basically equal to q prime divided by 2h, that is all. Okay. That is how you should remember this particular problem. Okay. So, now that we have found out what will be the average heat flux, we know what is the heat flux in general, or the total heat transfer. Okay. So, Nusselt number will be q double prime h divided by T naught minus T infinity into k, right. This is T infinity, okay, into k. So, therefore, it will be rho Cp by k g beta d cube T naught minus T infinity divided by 24 gamma. So, therefore, the Nusselt number becomes g beta d cube T naught minus T infinity divided by 24 gamma alpha. So, this is given as Rayleigh number based on the diameter, okay, a diameter of the separation between the two plates. Separation between the two plates was d. So, it is the Rayleigh number has been, so the length scale for the Rayleigh number has been taken as d instead of h. Okay. So, it is almost similar to the Reynolds number based on in a pipe flow, right. It is dependent on d, right. So, that is what is the value of your Nusselt number is going to be. Okay. So, the Nusselt number is kind of done. So, now one other thing that is important is that here also we see that there is no Grashof number coming into the picture, it is still Rayleigh number with respect to D that we are concerned about. Now, it is of course all these expressions are valid, okay, if and only if the entrance length yt that we have said earlier is less than h. This is the critical condition, right. That means if the two boundary layers are developing for a very long, or if the plate heights are kind of very small, that means they are short plates, right. Short is once again depending on how fast yt is actually developing. Okay. So, the thermal entrance length yt, this is the thermal entrance length, right, thermal entrance length yt, okay, is much smaller than the channel height h. Okay. So, yt should be much smaller than channel height h, right. So, that is one of the crucial conditions. Okay. So, can we establish now that what will be that necessary criteria, right, like we did in the case of your forced convection, that what was the entrance length dimensions. Okay. So, now for Prandtl number greater than 1, once again the two limits we are going to apply. So, yt into Rayleigh number with respect to yt, this is Rayleigh number with respect to yt, remember that this is almost equal to, the scale is actually d by 2 when the entrance length actually ends, because delta becomes of the order of d by 2. Okay. Okay, when y becomes of the order of yt, right, when this is in this regime, right, that the two layers are merging with each other. So, I am talking about this. So, this is y. So, when y approaches yt, okay, so delta should approach d by 2 also, right. So, that was the whole point, right, in the argument that we are putting forward over here, right. So, that is the first expression. For Prandtl number less than 1, this is yt, we already know it is with respect to the Boussinesq number, right, actually d by 2, right, so with respect to Boussinesq number, right. Now, what we can do now is that we substitute yt, okay, and put it back in the expression where we said that yt has to be less than h, we put it there, right, and establish an inequality of some sort, right. So, what we have done is that in the first case, okay, for Prandtl number greater than 1, what should we do? It will be d by 2, right, into Rayleigh number with respect to yt to the power of 1/4, right, okay, should be actually less than h, right. Okay. Now, similarly for Prandtl number, you can do the same thing for Prandtl number less than 1. Now, if you now take this particular parameter out, that means you try to convert it from the yt scale to the d scale, right, means you cast it in terms of Rayleigh number with respect to d, then you can show that this expression will now boil down as Rad to the power of 1/4 is less than 2 h by d to the power of 1/4. Okay. So, h by d with respect to the power of 1/4, that is how it will pan out, right. So, Rad, so Prandtl number less than 1 expression actually boils down to this. Similarly, Prandtl number greater than 1 expression boils down to this. Similarly, Prandtl number less than 1 expression boils down to Boussinesq number to the power of 1/4 less than 2 h by d to the power of 1/4. So, these are the two principal expressions that you get, okay, for this. Okay. In conclusion, what we can say that in order for this kind of flow to exist, that means your yt is much smaller, your Rayleigh number, okay, has to be less than certain aspect ratio, the geometric aspect ratio of the channel that you are concerned with here. Okay. This is the most crucial form that you will so your Boussinesq number or your Rayleigh number has to be such that they are lower than the aspect ratio of the channel, okay, or rather the aspect ratio of the channel in this particular case, right. So, if the Rayleigh number exceeds the order of magnitude as has been predicted by this expression, then of course you are not going to have any such flow, right. I mean your assumption on which you have based your velocity, on which you have based your Nusselt number expression, all are going to break down. Okay. So, the temperature assumption, so the fully developed assumptions fail, right, it is fail, okay, if the Rayleigh number exceeds okay, the order of magnitude dictated by h by d. So, what is h by d? H by d is nothing but the channel aspect ratio. This is crucial. Okay. So, that means therefore, when you actually design chimneys or all these kind of things, right, all these fins and other things, okay, you have to be sure that the Rayleigh number is such that this is actually satisfied. Okay. This is actually satisfied, that we have to keep in consideration, right. Okay. So, very high Rayleigh number and things like that can be actually pretty detrimental, okay, for the kind of problems that we are actually doing over here, right. So, so this part was very crucial. Okay. So, I hope this part is actually understandable, that it is h by d ratio, channel aspect ratio plays a very major role, and you can see that if this aspect ratio is very small, okay, that means the d is much larger than h, right. Okay. So, therefore, there the merger parameter, okay, may not be always satisfied. Okay. Similarly, you can have other such scenarios, okay, very short channels and things like that. Okay. Now, we move on to one very crucial thing before we slowly move on to our next parts. Okay. It is like basically the competition between natural convection, which I call as NC, and forced convection, which I am calling as FC, right. So, in a particular problem you can have what we call mixed convection. Okay. Mixed convection means that both the players are entering into the picture. So, there is, for example, a gradient that is created due to the whatever forcing that you are planning to do. So, okay, it could be flow, it could be pressure, it could be many other thing, but also the natural convection part cannot be ignored. Okay. So, there can be situations where the natural convection is so small, right, that it can be virtually ignored. Okay. But there can be also situations to the contrary, that forced convection is so small that it can be ignored. We are talking about situations in which the forced and the natural convections both are kind of important to a certain extent, right, but they may not be equally important, but on a relative basis they are kind of important, okay, with respect to each other. So, mixed convection and natural convection. Okay. So, when we are dealing with such a situation, okay, let us see the mechanism. Okay. So, if the mechanism is natural convection, which I call as NC, okay. So, therefore, the thermal distance or the thermal boundary layer thickness in the case of natural convection, that means as if natural convection was the only player in this particular situation, it is given by RA 1/4, right. This we already saw for Prandtl number greater than 1 limit. This was already there, right. Okay. So, the thermal distance between the fluid and this, okay, and the wall is basically given by that. Okay. Similarly, on the other hand, if the mechanism is forced convection, so this is corresponds to a buoyant wall jet, right. But if the mechanism is forced convection, right, that means there is a driver of a different sort, right. So, delta T forced convection or FC, okay, is given as y into Rayleigh number y, or sorry, Reynolds number y, Prandtl number to the power of minus 1/3 for the Prandtl number greater than 1 limit, right. This we already know from our boundary layer analysis in forced convection, right. So, which one will be the more dominant? Okay. That will be given by, if you look at these two quantities, these are the two thermal boundary layer thicknesses, right. So, whichever one is the smaller of the two basically should determine which particular mode is dominant, because if you remember your H, heat transfer coefficient, was dependent as 1 over delta T always, right. So, it is basically the inverse, that means smaller of the two is going to lead to a higher H with respect to the corresponding mode of heat transfer. So, if H of with respect to natural convection is higher than the H with respect to forced convection, so therefore, you will have a natural convection dominated situation, or in other words I can put it like this: delta T NC, if it is less than delta T FC, right, then it is a natural convection dominated problem, right. On the other hand, if delta T NC, okay, is greater than delta T FC, then it is a forced convection dominated situation. Okay. Got it? Okay. So, delta T NC is less than delta T FC, whereas delta T NC is greater than delta T FC means is forced convection dominated. If delta T FC is greater than delta T NC, it is natural convection dominated. Okay. So, it depends on which mode you are actually choosing, right, and these are all valid for Prandtl number greater than 1 situation, right. Now, if we cast it in terms of the non-dimensional numbers, so RAY 1/4 divided by Reynolds number 1 to the power of half, Prandtl number 1/3. Okay. Now, if this is greater than order 1, it is natural convection dominated. If it is less than order 1, it is forced convection dominated. So, it is given as a ratio of the two in terms of the non-dimensional parameters. Okay. So, this should be kind of pretty apparent, but what normally people do, if we look at this particular curve for example. Okay, so, what people have drawn over here is basically your Nusselt number, and basically instead of using the formulation that we just now advocated, they have done it in terms of Grashof number and Reynolds number. That is what we have done over here, right. Now, you can see in this particular situation, okay, that as this number, so for example, this is the total field, okay, which takes into account both natural convection as well as the forced convection. Okay. So, if you look at this this plots, okay, you will find that in these particular zones, okay, there is a kink in the curve, right, there is a knee, okay, there is a knee in the curve, okay, and this knee in the curve actually implies that so there are basically two asymptotic limits, right, which converge roughly around the value of around close to 1 in that particular order. Okay, it seems to converge around that particular point, right, but in and around that 1 order. Okay. So, and this is plotted of course with respect to Prandtl number. So, Prandtl number is going up in this particular situation, right. So, you have the two extreme limits, right. In one case it is pure free convection, in one case it is pure forced convection. You can see from the two legends. Okay. So, when it is so as you can see in this particular case, when it is free convection dominated to forced convection dominated, okay, you have this kind of a kink that develops in the curve. And so, in one extreme it will be forced convection dominated, in other extreme it will be free convection dominated. The reason why there is a kink and this kind of kink actually shifts over here, because this has been plotted with respect to Grashof number, okay, and not with respect to the parameter that we just now defined. So, in order to see what that leads to, okay, let us put that Grashof number y with respect to Reynolds number y square basically gives you Rayleigh number 4, okay, Reynolds number y to the power of half, Prandtl number to the power of 1/3 raised to the power of 4 and Prandtl number 1/3. Okay. So, the reason that you had this knee which was shifting, if you look at it once again, this knee was actually shifting, right, from here to here as a function of Prandtl number, basically comes because of this Prandtl number 1/3 dependence that we have included over here explicitly. Okay. So, that is not quite the correct thing to do, okay, because then you have a Prandtl number dependence now coming into the picture. If you draw the same plot as what Bejan did, okay, in terms of the new similarity variable, that means the new variable that we have done, okay, along with the Nusselt number, keeping everything the same, okay, you will find that that all for Prandtl number greater than 1, the curves fall on the top of each other kind of, right. Okay. So, there is and the kink is always of the order 1 in that range, okay, because that is where we go from pure forced convection to pure natural convection, right. And this we know that it is going to be 332, that is what we discovered earlier, if you remember, right, that earlier we found out that for flat plate that is what it is, like 0.332, okay, and here is the forced convection, the pure natural convection limit, and these are the two asymptotes, okay. But here the knee does not shift and they all fall around the value of around 1, okay. So, they all fall, the knee of all curves, okay, is at order 1, okay, on the abscissa. We show that we can estimate the Nusselt number with sufficient accuracy and efficiency, okay, and by doing this asymptotes, okay, we can actually predict that which mechanism is the most dominant of the two, but we have already established what the scaling arguments are going to be, right. Okay. So, for Prandtl number, so this actually covers the revised scaling argument, so to say. Now, if we look at the Prandtl number less than 1 fluids, okay, okay, so we can repeat the same assumption that we did earlier, okay. So, that is given by Boussinesq's number to the power of 1/4 and Peclet number to the power of half, okay. So, when this is greater than 0.1, this is natural convection, when this is less than 0.1, this is actually forced convection, or not 0.1 of order 1, okay. This is actually forced convection, okay. So, there has been a lot of work that has been done in this particular category, where we have revisited, we have just done a simple scaling argument, people have done more authentic and complicated solutions of the same thing, okay. But essentially it remains that whichever boundary layer is basically shorter or smaller, that basically gives you that mode should be the stronger of the two modes. Now, if you go to a situation where one mode is completely suppressed, then you have to show that that order is kind of very low compared to the other order, okay. So, there has been lot of work particularly by Sparrow, okay. So, Sparrow, University of Minnesota, and there has been a lot of progress on this mixed and natural convection that has been done by varieties of people from Lorenzo and others, okay, who have done more systematic solutions of these kind of problems and have tried to show that what it actually means, okay. So, but however, okay, from our perspective, okay, we can actually show that these kind of simple scaling can give you an idea that when which parameter actually defines the mode of heat transfer. So, this can be kept in mind, okay, when you actually start to solve problems, basically doing a back of the envelope calculations and try to find out how these things actually look like. Okay. So, see you in the next class.